So welcome everyone to the Oxford Bristol Set Theory Seminar, and this is the last talk of this term, and I'm delighted to introduce Joan Bagaria from Barcelona, and he's going to be speaking on some recent results on structural reflection. So take it away.
Thank you very much, Joel. It's great to be here. Thank you for the invitation and for the honor of being the last of the season. So today I want to give you an update on some notion that I introduced and started studying it a long time ago, about over 10 years ago now, that I call structural reflection. And this is the motivation for this is that it's a rather natural reflection principle. And the goal or the hope was when I started working on it to be able to show that many large cardinals, if not all of them, or at least some of the most well-known large cardinals, could be eventually shown equivalent to some form of structural reflection. Okay, this sort of a program has been quite successful, I think, and so today I just want to show you some of the most recent results. So my talk will have essentially two parts. The first part will be kind of overview of what we know about that and some relatively recent results with Trevor Wilson. And then the second part will be the most recent work, which is joined with Philipp Lücke, who is also here. Okay, so let me just begin. The general principle of structural reflection says the following. It says that for every, it's a schema, of course. It says that for every definable in the first order language of set theory and possibly with set parameters, class C of structures of the same type, there exists an ordinal that reflects this class, which means simply that for every structure in the class, there is one which lives below alpha, it's in V alpha, and there is an elementary embedding from B into A. So it's a reflection principle for definable classes. By the way, I'm just finishing now a survey paper covering what I will talk about today, plus quite a lot of other stuff. And hopefully I'll post it on the archive in 1 or 2 weeks. So you will have access to, if you are interested, you will have access to an expanded version of what I will be saying today. Okay, of course, sorry, this skips. Of course, to formulate this properly, you have to do it as a schema. So you formulate it for each n. So you look at the sigma n structural reflection principle, which says exactly the same, but only for classes of structures that are sigma n definable, and similarly for pi n definable, and so on. Now, if you just do a simple closing of argument, you can easily see that the sigma n structural reflection principle is actually equivalent to asserting that there is a proper class of ordinals alpha that reflect all classes, not just one by one, but all classes of structures of the same type that are sigma n definable with parameters in V alpha. And in the case of light phase, you just want one such alpha, okay? So, and the same for the pi bold phase pi n and light phase pi n. All right, so the first observation is that for sigma 1 definable classes, this principle is just provable in ZFC. And this is a simple argument. I will be using the notation Cn for superscript parenthesis n for the club proper class of cardinals such that V kappa is a sigma n elementary substructure of the universe. This is a pi n definable class. And what you have is that witnessing structural reflection for sigma 0 classes is the same as witnessing it for sigma 1 classes, and it's the same as being in C1, which means it's a fixed point of the Beth function. Okay, so that's just a rather simple Lowenheim-Skolem argument. Now let me remark that the pi n principle and the sigma n plus 1 principle are equivalent, both in the light phase and the bulk phase. And the reason for that is, let me just see if this works. Yes, the reason for that is that if you take, if C, you have a class that is sigma n plus 1, then let C star be the class of it's the class of all structures of the form V alpha. Sorry, I ran out of slide. V alpha epsilon A, where A is in C, and A here is a constant. So A is in V alpha, and alpha is in Cn. So now this class now is pi n definable, and if you have reflection, structural reflection for C, even only if you have it for C star. So this is the reason. This also tells you that, in fact, all the structures that matter are, we are talking about definable structures in general, but the ones that really matter are those of this form, of the form V alpha together with epsilon and some distinguished element of V alpha. So for classes of structures of this form that are definable with some degree of complexity, allowing for set parameters. That's the idea. Okay, let me just, right. So what do we know about that for, okay. So for sigma 1, this is provable in ZFC. I don't know why this skips. Okay. We know that for sigma 1, this is provable in ZFC. So how about for more complex classes of structures? So in general, this is the general result. Well, the structural reflection principle as a schema, namely pi n SR for all n, it's equivalent to the light phase form, also equivalent to the existence of a Cn extendable cardinal for every n. And this means the following. If you are familiar with the definition of extendable cardinal, this is just the same, but you only require in addition that the image of the critical point is in Cn, okay? So structural reflection is just equivalent to the existence of a proper class of such Cn extendables, or just one Cn extendable for each n. And this is also equivalent to Vopenka's principle. And Vopenka's principle is, let me remind you, is the schema assertion that if you have any proper class of structures of the same type, you have two different structures in the class such that one is elementary embeddable into the other. That's just one of the many different formulations of Vopenka's principle. So all these schemata are equivalent. Of course, when you look at the proofs gives you a lot more information. For example, for pi 1 definable classes, the structural reflection principle is equivalent to the light phase is equivalent to the existence of a supercompact cardinal. For pi 2 is the equivalent to the existence of an extendable cardinal. And then for pi n in general is just equivalent for n bigger than 1. The existence of, by the way, extendable is the same as C1 extendable. So for C2 extendable, you get the equivalence with pi 3 structural reflection, and so on. Yes, so you have a whole hierarchy here from supercompact, that's pi 1, to Vopenka's principle. All right, so those were the first promising results. And then the question is, okay, how about large cardinals or reflection principles that live in the region below a supercompact, right? So this covers the region from supercompact to Vopenka, but how about below that? Well, then we studied with Trevor Wilson 2-3 years ago, started studying reflection for products. And well, here is I mean, in my paper with Trevor Wilson, we didn't formulate it like this, but there's another similar principle. But anyway, so this is how I formulate it today. It's what I call the product structural reflection. It's similar as the structural reflection, but it's a version for products. So it just says the same. So if for every definable class of structures, C, all of the same type, then there is an ordinal that product reflects C. What does that mean? It means that if you pick any structure in C, then you can find an elementary embedding from the product of all the structures in your class of rank less than alpha into some product which contains your structure A as one of the factors. Okay. So you want it just for products. So instead of for every A in the class, there is a B also in the class below alpha and an elementary embedding. Now you're saying, okay, for every A in the class, I can take the product of all the structures of rank less than alpha and embed this product elementarily into some product of which A is one of the factors. All right. Okay, so what we prove with Trevor is the following equivalence. Again, these are schemata. So the product structural reflection, which is pi n product structural reflection for Ln, it's the equivalent to the light phase version of this. It's also equivalent to the existence of a pi n strong cardinal for every n, which I will define right away. Also to the existence of a proper class of pi n strong cardinals for every n, and also equivalent to the statement or this wooden, which I will also tell you in a minute what it means. This is also, with Trevor, our initial motivation was to investigate or to study something called the weak Vopenka principle. And Trevor showed that weak Vopenka principle is equivalent to the statement or this wooden. But then we carried out this level by level analysis, and then we found that we have an entirely similar structure here as we had before with Vopenka principle. But now it's at the level from strong to wooden, whereas before we had the same in the interval, let's say, from supercompact to Vopenka. Okay, so let me tell you what pi n strong. So in general, for gamma definability class, I mean some sigma n or pi n. A cardinal is lambda gamma strong if for every gamma definable without parameters class A, there is an elementary embedding from V into some transitive class M with critical point kappa. V lambda is contained in M, and A intersected with V lambda is contained in the image of A. So if you are familiar with the notion of A strong cardinal, which is used as a characterization of woodenness, then you will see that this is the same, but now here we want that so kappa is A strong simultaneously for all classes A that have a certain complexity, right? Certain degree of complexity in their definability. Yeah, sorry. So we say just it's gamma strong if it's lambda gamma strong for every ordinal gamma.
Did you insist
right.
that J of kappa is bigger than lambda as part of this definition, I guess?
You get also this for free. Yeah. Okay. So what does what does ord is wooden mean? Well, it means that for every definable class, there is some alpha which is a strong, meaning that for every gamma, there's an elementary embedding from V into a transitive class M with critical point alpha. J of alpha goes above gamma, V gamma is contained in M, and A intersected V gamma is just J of A intersected V gamma. So this is just the definition of A strong, but now that characterizes a cardinal being wooden, but instead of looking at subsets of V delta, where delta is the wooden cardinal, here we just look at definable proper classes. Okay, so if delta is a wooden cardinal, then in V delta satisfies that ord is wooden. That's the idea. All right, so this product structural reflection allows us to characterize in those terms the cardinals ranging from strong to wooden. Now, when we look at any question, I thought, oh, okay. Please feel free to ask anything. Okay, so when you look at the proof of these results, so for example, when you prove that if kappa is pi n strong, then pi n product structural reflection holds, then okay, then you show to do that you show that for every pi n definable class of structures of the same type, and for every beta, there is a set of structures of the same type that contains all the structures in your class up to rank beta, and there is an elementary embedding from the product of all the structures in your class of rank less than kappa into the product of this set S. But not only that, this is a special kind of elementary embedding. So what you get is a lot more information from the fact that kappa is strong. The embedding you get has two additional properties that are quite interesting. This embedding is not only elementary, but it's what I call faithful, which means that every element in the product of C intersected V kappa gets extended, right? So, and the second condition is that if you take an element of the product of C intersected V kappa with the property that for different coordinates A and A prime, if f of A is contained, if A is contained in A prime, then f of A is contained in f of A prime. Okay, so here A and A prime curly with curly type means the structures. A and A prime with just non-curly means the universes of those structures. Okay, so the embedding you get from a pi n strong cardinal, it's not only elementary for the products, but it also has these two additional properties. It's faithful and it preserves subset the subset relation, so to say. Okay. Now, so what you get is that the general principle of product structural reflection is equivalent to this one, in which I call the second version, namely that there is a cardinal kappa such that for all gamma definable classes of structures C of the same type, and for every beta, there exists a set of structures of the same type that contains all the structures up to beta, and there is a faithful and subset chain preserving elementary embedding, okay, of the products. This is equivalent, so the previous version of the principle holds even only if this principle holds, okay. But the advantage of this second formulation is that now you can give an outright characterization of strong cardinals and pi-n strong cardinals. So a cardinal kappa is a strong, even only if it witnesses this principle in the second version. If you only have the first version, you know there is a strong, but the strong cardinal need not be the same that witnesses the principle. It might be smaller. Okay, so those two additional requirements of faithfulness and preservation of chains, what they do for you is that they guarantee that it's exactly the same cardinal. So the strong cardinal is exactly the one that witnesses this principle. Okay. And it's exactly the same as it's the same thing for the pi-n strong and the pi-n product structural reflection principles. Okay, so the proof of our result with Trevor Wilson in this somehow refined version is I mean, it's a bit involved because you need to, from the difficult part is to get from this product structural reflection to get the strong cardinal. And for this, you need to produce some extenders that then they cohere in a very nice way, and you take the direct limits and so on. And then the faithfulness the faithfulness property makes sure that the critical point is what you want. Is the cardinal you want, not something smaller. And the subset chain preserving is used to get the coherence of all these systems of extender embeddings. Anyway, I will not give more details because I want to go into more results. Sorry. Yes. Right. Okay, so there is another natural form, or if you want, if you compare if you look at the second version of the product structural reflection principle, it's very natural to ask, well, why couldn't you just instead of saying that, you know, for any structure in your class you can find an elementary embedding from the product of all structures in your class of rank less than alpha into some set that contains your structure as a factor. Well, this is okay, but why not just simply say that for every structure in your class there is some ordinal beta bigger than the rank of A, and an elementary embedding from the product of all your structures up to rank alpha into the full product of all the structures in your class up to rank beta. So it's just product reflection from some bigger rank into alpha. Yes, of course, this is the same as saying, instead of saying for every structure in the class C, is just this is the same as saying that there is a proper class of betas with this property. So we're just saying that. By the way, I didn't mention it at the beginning, but whenever I say a class, I always mean a proper class. Otherwise, all this is absolutely trivial. Yes. So this is so this is just equivalent. Again, let me say it again. This is just equivalent to saying that there is a proper class of betas such that there is an elementary embedding from the product of all structures up to level to rank alpha into the full product of all the structures in your class up to rank beta. Okay, so this is somehow the most natural product reflection principles. So let's see what happens with this. Well, it turns out that this is also equivalent to some known large cardinals, maybe not as well known as strong cardinals or wooden cardinals, but there's this notion of CN superstrong cardinal that was studied in a paper by Jinglun Tsai and Kostas Tsaprounis, published in 2019. So a cardinal is CN superstrong above lambda, for some lambda greater or equal than kappa. If there is an elementary embedding from V into some transitive class M with critical point kappa, J of kappa is sent above lambda. V sub J of kappa is contained in M, so this is the super strongness condition, and J of kappa belongs to Cn. Okay, and kappa is Cn globally super strong if it is Cn super strong above lambda for every lambda. Okay, these cardinals are not very large in the large cardinal hierarchy, because if kappa is Cn extendable, then there are many Cn globally super strong cardinals below, and consistency wise is weaker. It's below the existence of a one extendable cardinal. So we are still at this below Vopenka principle. But we do have a similar characterization. So again, these are schemata. So this strong product structural reflection is equivalent to the existence of one Cn globally super strong cardinal for every n, or a proper class of them. So it's exactly the same pattern. So these are slightly stronger product reflection principle, which can be seen to correspond exactly to those Cn globally super strong cardinals. Okay, let's see, how are we doing? Good. Again, when one looks into the proof, then we also have, I will skip this, I will go quickly on that. You also have this faithfulness and chain preserving properties, which allows you to characterize exactly those cardinals. So when you use the second version, which it's equivalent to the first, but for a particular cardinal kappa, if you use the second version, then this gives you exactly that kappa is Cn globally super strong. All right. Okay, so that was the first part. So now I will discuss. I will show you some results that that we obtained with Philipp Lücke. This was done in the last half a year or so. And there is already a paper, a preprint at Archive that you can look at if you are interested. Okay, so the idea of our project was to look for some principles of structural reflection that were natural, simple, and nevertheless give you a lot more strength than Vopenka's principle, that go beyond Vopenka's principle. Yes. Okay. So this is what the kind of principle we have been looking at. This is something we call exact structural reflection. What does that mean? It means that for infinite cardinals kappa less than lambda and a class C of structures of the same type, the principle says that for every structure in your class of rank lambda, exactly of rank lambda, there exists some structure in the class of rank exactly kappa and an elementary embedding from B into A. Hence the name exact, because we require that those structures must have exactly rank lambda and rank kappa. Again, I mean, this is, we are talking about definability, definable classes. So we just consider those principles for a given definability class, one of the sigma ends or pi ends, and allowing for some parameters, maybe from some set or class of parameters. But now the difference with respect to previous notions of structural reflection is that here one needs to distinguish between classes that are closed under isomorphisms for isomorphic copies. In the previous, for the previous principles, this does not make any difference, but here it does. So, and we will see why in a minute. So we consider the same principles, but when we just restrict to those classes that are definable with some degree of complexity, but that are also closed under isomorphic copies. Right, so here's the first result. For every singular cardinal kappa, and I want to stress this, so kappa has to be singular. The following are equivalent. Kappa is a limit of supercompact cardinals. The principle of exact reflection holds for pi1 definable classes with parameters in kappa, and it holds for a proper class of cardinals. And the sigma 2 exact reflection with parameters in V kappa also holds for a proper class of cardinals lambda.
Jean,
and I emphasize that, yes?
Can I ask a question about this exact reflection? So you say the structure, the structures of rank kappa and lambda. And so what do you mean by that exactly? You mean in the cumulative hierarchy, so that the structure as a
Right.
tuple of domain and relations and so on, that tuple is an element of V kappa plus 1? Or what do you mean exactly about the rank?
Yes, yes, that's what we mean. That the rank is exactly it's the rank of its domain.
But if kappa is a cardinal, oh, the rank of the domain only.
Yes, yes,
Okay,
yes.
fine. As a set, okay, that's fine.
The rank of the domain, yes, yes,
Okay.
yeah. Mm-hmm.
Thank you.
Yeah, sorry. Okay, so this is so this characterizes for singular kappa being a limit of supercompacts. Okay. Now and this is for pi1 definable classes closed under isomorphic copies, or sigma 2 definable classes closed under isomorphic copies. If we look at more complicated classes, then one needs to use a similar notion as CN extendibility, but which is a bit weaker. And this may be a bit too technical, so I don't want to spend too much time on it, but that's we have this notion for mu less than lambda and a cardinal less or equal than mu. We say that this cardinal is mu lambda Cn extendable if there is some cardinal in Cn plus 1 in the interval between mu and lambda, and there is an elementary embedding from V lambda into some V eta with critical point kappa. J of mu is sent above lambda, or it can be lambda, and J of nu is in Cn. So this is a slightly more complicated version of Cn extendibility, but that's exactly the notion that one needs here. And we say it's mu infinity Cn extendable if this holds for a proper class of lambdas. So it's not difficult to see that every Cn extendable cardinal is mu infinity Cn extendable for every mu or equal than kappa. Okay, so so this is kind of a weakened version of Cn extendability that is technical, but it's exactly what you need in this context, because that's what you can prove. You can show that these are equivalent for every singular. Again, I stress the fact that this for singular cardinals kappa, that kappa is a limit of kappa infinity Cn extendable cardinals, or that the pi n plus 1 exact reflection or sigma n plus 2 exact reflection holds for a proper class of cardinals lambda. And this again is only for isomorphism closed classes. Okay, so so in particular, just look at the particular case, a singular cardinal kappa is a limit of extendibles even only if this exact reflection holds for pi two definable classes that are closed under isomorphic copies. Okay. So you see, we had for pi1 or sigma 2 was a limit of supercompacts. For pi2 for pi2 or sigma 3 is a limit of extendibles and so on. And then you have this hierarchy with the corresponding kappa infinity Cn extendibles. Again, you have the same kind of structure or hierarchy. Okay, but this is not good enough, because actually we are still, our motivation was to go beyond Vopenka's principle, but this does not go beyond it. In fact, we are still there, because Vopenka's principle is equivalent that we have this exact reflection holding for all classes of structures closed under isomorphic images, or the same saying that there is a proper class of cardinals with the property that all pi n definable classes with parameters in V kappa satisfy this exact reflection. So we are still in the domain, or we are just still within this Vopenka principle setting. But now, if we look at those principles for regular cardinals, remember we had those theorems, but they work for singulars. But if we look at those principles for regulars, or for arbitrary classes of structures of a certain degree of complexity that are not necessarily closed under isomorphic images, then we get much stronger principles. Let's see. Okay, to show this, we need to introduce some, again, a kind of technical notion of large cardinal, which we call weakly and exact. So we say that kappa is weakly and exact for a cardinal lambda bigger than kappa, if for every, let me just draw a picture, okay? Let's see, how is this, if I can do this. So, okay, here. So we have kappa here, whoops. Sorry, I'm not so used to drawing with that. So we have kappa, have lambda here. Then we have some lambda prime above this, which is sufficiently correct, is in Cn minus 1. And then we have some transitive set M, which contains V kappa and actually kappa as well, right? And we have an elementary embedding from M into H lambda prime that sends kappa to lambda. And not only that, but if you pick anything A at level V, and you pick any subset of V lambda, then this is in advance. If you pick such thing, then you can find such an embedding for which A is in the range. Okay. Okay, so if we, in addition, we require that the critical point of the embedding is sent to kappa, then we call it parametrically inexact. Let's see if this works. Let's see. Okay, right. So that's the large cardinal notion that works here. Let's see. I'm done with that. Right. Sorry. So here's the theorem. The following are equivalent for all cardinals kappa and all n greater than 0. Kappa is the least regular. I emphasize the fact that it's regular cardinal, such that the exact reflection holds for pi n definable classes closed under isomorphic copies. kappa is the least cardinal that satisfies exact reflection for pi n definable classes, even with parameters in V kappa. Kappa is the least cardinal that is weakly and exact for some lambda, or is the least cardinal that is weakly parametrically and exact for some lambda. So those are the cardinals that correspond to those principles, these exact principles for regular kappa or for classes that are not necessarily closed under isomorphic copies. Now let's see, by the way, a similar thing holds for, these are the pi n classes. For the initial reflection principles I mentioned at the beginning, for the general reflection principle, for pi n or for sigma n plus 1, those are equivalent. Here they aren't, they are not. Okay, so here for pi n or sigma n plus 1 are quite different, and for sigma n plus 1, you get a stronger notion. And the stronger notion corresponds to this notion of large cardinal, which it's similar as before. So it's the same thing as before. We have kappa here, we have lambda, we have some lambda prime sufficiently correct, more correct than before. And now instead of a transitive set M, we have something that is not transitive, is some X that is an elementary substructure of some sufficiently correct H kappa prime. But we have the same thing. We have this elementary embedding that sends kappa to lambda. And we can find, if you pick subset of V lambda in advance, then you can find you can find such an embedding with A in its range. And if the critical point is sent to kappa, then we say this cardinal is parametrically inexact. So it's very similar as before, but now here we have this X, which need not be transitive. Before we had an M, which is transitive. And this X is more, the lambda prime has a higher degree of correctness and so on. I will not dwell on that because it's similar as before, but this is the exact large cardinal notion that gives you the sigma n result. So that's the theorem for the sigma n. So all these are equivalent. Kappa is the least cardinal that witnesses this exact reflection for sigma n plus 1 definable classes. Also the same with parameters, and it's also the least n-exact and is the least parametrically n-exact. Okay. Now, how strong are those cardinals? Are we still within the Vopenka principle realm, or have we gone beyond? Well, we have, because if kappa is less than lambda cardinal such that either kappa is parametrically 0 exact for lambda or weakly parametrically 1 exact for lambda, then there are many almost huge cardinals below kappa. Okay, and we know that this is the consistency strength of an almost huge is strictly bigger or stronger than the consistency strength of Vopenka's principle. So if kappa is almost huge, then V kappa satisfies Vopenka's principle. And also we have that if kappa is parametrically 0 exact for some lambda, then kappa is almost huge itself. Okay. So these exact reflection principles in the either for regulars or for classes that are not necessarily closed under isomorphic copies, this leads us beyond Vopenka principle in terms of strength. Also, if kappa is huge with target lambda, so that the J of kappa is lambda, then kappa is weakly parametrically one exact. And a consequence of this is that the exact reflection principle for pi1 definable classes with parameters holds, with parameters in V mu, holds for some mu less or equal than kappa. Okay. So hugeness implies that we have this degree of structure of exact reflection, exact structural reflection for some cardinal less than or equal to kappa. And also it's true that at kappa, sorry, it's true that in V lambda, this is true for kappa itself. So anyway. However, if kappa is the least huge cardinal, then kappa is not one exact for any cardinal lambda. Okay. So here we are still, so here we are in between. So lower bounds are almost huge cardinals. Upper bounds is a huge cardinal. Okay, so can we go beyond that? Well, if we, that was for pi1, but if you go, if we try to see what happens with that was for one parametrically exact or okay, or weak for one parametrically exact. So if we have a too huge cardinal, then we have a similar thing. So if kappa is say a too huge cardinal, then we can find some cardinal lambda bigger than kappa and rho bigger than lambda, such that in V rho, which is rho is inaccessible, it's a model of ZFC, and in this model, kappa is weakly parametrically and exact for lambda for all natural numbers. So this gives us a real upper bound for weakly parametrically and exact cardinals. Okay. If we want just not, I mean, even a much better upper bound, better in the sense that we get something a lot stronger. So if we have an I3 embedding, so an elementary embedding from some V lambda into V lambda, some V delta into V delta with delta limit, then, well, in this situation, we know that, okay, so I don't know where can I draw here, but if this is V delta into V delta, we know that the critical sequence, so if kappa is a critical point and we look at the critical sequence, this is all this sequence is cofinally delta. So now if we pick any element in the sequence, so any element in the sequence is parametrically and exact for all the further terms in the sequence. So we have in V delta, there is a proper class, yes, of cardinals that are parametrically and exact, and they are solved for a proper class, so to say, of cardinals lambda. So this gives us the really upper bound for this type of cardinals that we call parametrically and exact, and therefore also for the weakly and exact, or parametrically weakly and exact, and so on. So an I3 embedding is just a real upper bound for all these notions. So can we go beyond that? Sorry, let's see. Yes. Okay, so to go beyond that, am I doing with time? Okay, good. So to go beyond that, we consider a sequential form of exact reflection. And let me just give the definition. So now we are looking at the first order language containing some predicate symbols, so some sequence of predicate symbols sequence of length at most omega. So it can be finite or of length omega. And now we say that the sequence of mu of cardinals with supremum mu structure has type mu, mu arrow with respect to those predicate symbols. If the universe has rank mu, mu is the supremum of the sequence, and the rank of each one of these predicates in the structure A is exactly mu I for all I less than eta. Okay, and then we define similarly as before. So this is the exact reflection, but now it's not just a reflection from one rank lambda to the rank kappa, but now this it's about a sequence of it's a sequential kind of reflection. So we are just saying if we have a sequence lambda arrow of lambda I for I less than 1 plus eta. So this is we write it this way. Eta can be here. Well, we don't need it in the definition, but think of eta being some finite ordinal or omega. Then the principle of reflection, of exact reflection, says that for every structure, for a given class of structures of this type, okay, for every structure in the class of type, so we start with, let me draw a picture because it's going to be easier. Sorry. Yes, so we have this situation here. So we have lambda 0, lambda 1, lambda 2, sorry, lambda 2, and so on. Yes. And the supremum is lambda. Yes. Supremum is lambda. And we pick some structure of type. So we look at the I plus 1. Yes. So so this goes like this. An embedding. Well, I don't know how to draw this. So okay, so you look at the types, a structure of this type, and now you have a structure of this type. So sorry, you start, bad drawing. So let me just do it again. Sorry, let me do it again. So let's see. Lambda 3 and so on. Let's do lambda 4. Okay, let's do a finite case. Yes. So then we have that for this, if you have a structure of type this with only 3 predicates, then you have one of type like this. So this reminds, of course, Chang's conjecture, right? If you take lambda to be, you just take aleph 0, aleph 1, and aleph 2, well, then this is just Chang's conjecture. Just that for every structure of type omega 2, omega 1, you can find an elementary substructure of type is usually represented like this of type omega 1 omega. Yes. So this is just a strong generalization of Chang's conjecture and is formulated for definable class of, by the way, for Chang's conjecture, the class to which you apply this is the class of all structures the class of all structures with two predicates in the language with 2 additional predicates. Yeah. Okay. So this is just a generalization of Chang's conjecture. These kind of principles have been studied quite thoroughly by people, especially Matt Foreman and other people. So, okay, so for this, we also have the notions of, I'm not doing very well with time, so maybe I'll just skip this quickly. For this kind of sequential form, we also have the corresponding sequential forms for the weakly inexact and exact cardinals. And we have similar results, but in this sequential way. Yes. So I will skip this because similar as before. Okay, sorry. Yes, but and we have these equivalences. Okay, so this is, however, only for finite sequences. Okay, so for when eta is a natural number. So the least cardinal, such that there exists an increasing sequence or lambda vector of cardinals, such that the first element of the sequence is kappa, and exact reflection for this sequence holds for all pi n definable classes. This cardinal is exactly the least cardinal that is weakly parametrically and exact for the sequence. Okay, so this notion of weakly parametrically exact cardinals for sequences corresponds exactly to this exact reflection principle for sequences. And the same holds for the sigma n case, and now we have the inexact cardinals for sequences. So it's an entirely analogous thing. The proofs are a bit harder because working with the sequences poses additional technical problems. But anyway, the situation is completely parallel, completely analogous. Now, how strong are those principles and those cardinals? Yes. Well, if kappa is an n huge cardinal, then which is witnessed by some embedding from V to M, then kappa is weakly parametrically one exact for the sequence of for the critical sequence, which you iterate the values of the critical point. And if kappa is a cardinal and we have such a sequence, then such that kappa is either weakly one exact for the sequence or zero exact for the sequence, then some cardinal less than kappa is n huge. So here we are for one exact or for zero exact, for weakly one exact or for zero exact, we are at the level of n huge cardinals here. Okay. Well, let's see what happens for the n exacts, or can we go further than that? Are these cardinals consistent? Well, here's another fact or proposition that if kappa is either weakly one exact for this is for infinite sequences, okay? This is for infinite sequence, lambda of length omega, lambda vector of length omega. If kappa is either weakly one exact for the sequence or zero exact, then there is an I3 embedding. So for infinite sequences, lambda of length omega, then we get something really strong. We get an I3 embedding, okay? And also, if kappa is either parametrically weakly one exact or parametrically zero exact, then we have many critical points of I3 embeddings below kappa. So you see now we are approaching the upper ranges of the large cardinal hierarchy with these sequential forms of exact structural reflection. And let me finish with this another fact, that if we have now an I1 embedding, so this is an elementary embedding from V lambda plus 1 into V lambda plus 1, then kappa, the critical point of this embedding is weakly parametrically one exact for some sequence. Okay, so for many sequences. So let's look at one particular case. Let's look at the case when case 1. Then we have that kappa is weakly parametrically one exact for the iterates of the critical point, and therefore by the previous results I mentioned, we have that we have exact structural reflection for pi1 definable classes of structures and for this infinite sequence. Okay, and this we get it from this I1 embedding, but this is where we stop. So we don't know more than that. So let me just finish with some open questions. That's my last slide. Okay, so the first question is about the exact reflection, not the sequential one, but just the plain exact structural reflection. We don't know if the existence of a huge cardinal implies this principle for sigma to definable classes without that are not necessarily closed under isomorphic copies. We know it's true for pi1, but we don't know if it implies it for sigma 2. We don't know either this characterization of the least cardinal that satisfies exact reflection with the least and exact cardinal. This works for sequences lambda that are finite, but for infinite sequences, for sequences lambda sequences that have length omega, we don't know this. There's the proof breaks down in the case of omega sequences. So we don't know if kappa is the least cardinal that satisfies exact reflection for an omega sequence for pi n definable classes, whether this cardinal is weakly parametrically inexact for this for some sequence, any sequence. And finally, we don't know if all this is consistent when we go beyond pi1 definable classes. So for sigma 2 definable classes, this might just be inconsistent. Okay, so it may just be outright inconsistent. We don't know that. Anyway, so I'll finish here. And the final thought is that, okay, so these principles of structural reflection, and in particular, these exact forms, if you push them a little bit, not too much, leads you all the way up to the large cardinal hierarchy and possibly beyond what is now more or less accepted as consistent. So this might go beyond I1 embeddings and still be consistent because they don't seem to be falling into Punnen's inconsistency. So this makes it, I think, quite interesting. Anyway, okay, that's all. Thank you.
Thank you very much. Let's all thank Joan for a great talk. And if there are any questions, then just put your name in the chat or speak up. Does anyone have a question? Okay, I have some questions. So, Joan, I'm a little curious about what your theory of classes is. It seems, I think you're working in a theory where every proper class is definable or something like that.
Yeah, that's right. Yes, yes,
so
yes.
For you, Vopenka's principle is only about definable classes.
That's right. Yes, yes.
Okay, so
exactly,
I'm a little bit curious about this because, for example, when you defined ord as wooden, you say for every class there is this other class. Okay, and that becomes problematic. But unless, I guess you
right.
translate it into extender ultra powers or something like that.
Well, the equivalence I showed that this is equivalence of a schemata, right? So a schemata holds even only if the other schemata holds. So ord is wooden.
Here, even ord is wooden is not prima facie a schemata at all because you have alternating class quantities.
Well, but it is if you restrict it to in the way I defined it. I consider the proper way of defining it. That's I think what I wrote is that for every n. Okay, for every natural number n, you consider the statement that for every sigma n definable class, so on and so forth, right? So you have all this schema, this omega. I'm sorry, I don't hear you well.
That's exactly what I'm objecting to. I mean, I think it's easy to fix, but you didn't say anything about it, which is why I'm asking. You want to say for every sigma n definable class, there is an elementary embedding. That's a class quantifier, right? So you should say there is an extender such that the ultra power witnesses it to make it a first order quantifier.
Right. Yes, sure. Yes. Yeah, you're absolutely right. Yeah, that's the proper way of, yeah.
Okay, I have another question, and that is about this closed under isomorphic copies. So you referred to it a few times, but you didn't really, or unless I missed it, is it because you're using that property in the exact versions because you need to control the rank exactly?
Yes, right. Yeah, because this is
has the wrong rank, and so you may need to change the rank. Is that how?
Right. Yes, that's a problem. Yeah, there's because if you only look at the rank, that's what happens in the case of singulars, right? Because then you could have something small which nevertheless has this rank. Yes. So you have to be careful with that. Yeah, that's the reason. Yeah, and the fact that you have closure under isomorphic copies is because you can maybe you cannot find a structure if the class is not closed under isomorphic copies. Well, maybe there could be one isomorphic of that rank, but maybe it's not there. Yes, it's not in your class.
Padded the rank somehow to make it have the rank 6 higher or something. I mean, you could play
right. Yeah.
Okay, good.
Yes.
I think I understand that.
Yeah.
So are there any other questions?
Yeah, I could ask something.
Go ahead.
So John, does any of this reach into or interact with recent work on choiceless models?
Well, that's a very good question, and it's a very good question, and I think that Philipp Lücke and I want to look into that next, because that might be interesting to consider this kind of reflection in the non-choice context, and trying to reformulate Berkeley cardinals or cardinals of this sort in a similar form. This is as far as I know completely virgin territory. So this something that probably Philipp and I will look into in the next few weeks. But yeah, it's definitely
interesting. Yes,
that's an interesting point. Yeah, thank you.
Oh, thanks.
Any other questions? Okay, in that case, let's thank Joan again for an excellent talk. Really interesting. Thank you so much. And
thank you all. Thank you.
This concludes the Oxford Bristol Set Theory Seminar for this term. I guess we'll all have summer break and start up again in Michaelmas term next autumn, I think. So please come back. And
okay. I think I'm just going to get a beer in your honor, since we cannot have it together.
That's right. Yeah. Okay. So
okay.
Have a good evening.
Okay. Bye, everyone.
Pleasure to see you.
Bye, everyone. Thanks, Joan.
Bye.
Bye.
Bye. Bye. See you.